Hi, I'm Jeff Cogswell. Today here at Go Parallel, I'm going to talk about the Xeon Phi Coprocessor and specifically its offload model and how to deal with shared memory. Now, the Xeon Phi, remember, is basically a separate computer that you install inside your own computer that becomes known as the host computer. And the Xeon Phi has its own memory separate from the memory in your host computer. Now, what that means is you can run code on your host computer, and with the help of a runtime library, you can then move that code at runtime over to the Xeon Phi coprocessor and start it executing over there. And the problem, though, that you run into there is, let's say you have some C++ instances of classes, and you've created those on the host computer. And then you have a function that you want to call over on the Xeon Phi. So you use the runtime library to transfer that function over to the Xeon Phi. And now we've got a problem, though, because those objects you created are still over on the host computer. Well, the runtime library gives you a way to copy those objects over across to the Xeon Phi's own memory. Then the function over there can work on them, operate them, change them, do whatever it needs to, and when it's done, send those objects back to the host computer. Now, this all sounds fine and dandy, but there's a fundamental issue there, and that has to do with how the memory is addressed, what the addresses are of those pointers. Inside your C++ objects, you might have a pointer to another object, and that pointer is basically a number, an address in memory. Now, if you're moving that between memory from the host to the Xeon Phi, what that means is those numbers need to be the same. So that's what I'm going to look at right now. Now, this is just a brief overview, and at the end I'll point you towards some resources where you can get some more details on this. So, let's talk for a brief minute about virtual memory. Now, when your computer is running and you've got your operating system running, such as Windows or Linux, you can have multiple processes running. Now, in the older way of say, the old DOS programs, you had your physical memory, and if you have more than one process running, each would get a chunk of that physical memory. Well, using a technique called virtual memory now, today that's no longer the way it works. Every process has what it sees as a full range of memory, from 0 on up to the limit of whatever can be addressed. And that may well be more than what's available in the physical memory. In fact, it usually is. And it can span hundreds of terabytes. And so you're not actually using all of that memory, but you have all that addressed. And portions of that will point to specific locations in the physical memory. So you've got up here your process, and here's some memory addresses. These might point over here to somewhere in the physical memory. Now, you might have another process running, and that also has its virtual memory space. And it can have the same numbers over here. But if they're running together, the 1, 2, 3, 4 in this one might point to a different place in physical memory. And what that means is that data is actually in a different position in physical memory. Now, when you're switching between processes, the operating system can actually save some of this memory to disk. And then when the process starts up again, it pulls that memory off disk back into physical memory. And that's all handled by the operating system. And the processor uses various techniques to notify the operating system that it needs to pull that memory data in and out of the disk and into physical memory. And that all works fine. And what that means is your process has a whole range of memory addresses. They're redirected to different places in memory. And over on your Xeon Phi, it's going to be the same situation. So what they do is the memory that gets mapped inside your host process, all those numbers will match the memory locations inside the Xeon Phi. And then you use the runtime library. When you copy over your object, your instances, they'll get copied over, and when they land over on the Xeon Phi side, they will keep the exact same numbers, even though it's on a completely different, really a different computer. Now, the only thing you've got to be aware of, though, is how you can do that in C++. In C++, there's two ways to store your data, and one is on the stack and one is on the heap. And stack effectively means your local variables. Heap means memory that's addressed through pointers. And what we've got here is a sample here. This code creates an instance of my class and stores it in the variable x. We're not using any pointers, so this is just a local variable, and it's stored on the actual stack. Now down here, x is calling new, and we're creating a new instance of my class out on the heap. And that's the difference. This code down here is allocated on the heap, and that code can easily be copied across to the Xeon Phi. Now I'm going to borrow some slides here from Intel. Let me switch to them real quick here. This is the Intel Xeon and Xeon Phi webinar, and it already happened. It happened a year ago, but you can still read see all the presentations on here. And I've got one on here by Robert Reed, and down here he's talking about what I was just saying, that you have the same address range over on the host and over on the Xeon Phi's coprocessor. And what he's got here are several examples of Silk, actually, where you can use some Silk keywords to specify that the function can be copied across and that the data can be copied across. And right here we can create a class and use the same class syntax that you normally would, but you throw in the Silk shared, and that tells the compiler that the instances created with that class will be shared across to the Xeon Phi coprocessor. And when you create an instance, here we've got a pointer. In this case, they're just pointing to an int. In our case, we were pointing to an instance of my class, but it's the same idea. This is a pointer, and you throw in the Silk shared, and that tells the compiler to create code so that the data that pointer points to can be copied across. And the system is smart. You can have entire vectors in the sense of not of SIMD vectorization, but object vectors, arrays, and all the standard library classes and whatnot. You can make instances of those, and all of it will copy across just fine. You can have complex classes, objects with pointers to other objects and whatnot, and it will take care of it and copy everything across smoothly. And your functions have to be surrounded by a pragma offload attribute and pragma offload attribute, and that function will then be copied across. And they've got more examples down here where here they're actually calling the function. Now here's the name of the function and its parameters, and you call silk offload, and x is just what the function returns is stored in x, and that tells the runtime library to go ahead and copy that function across to the Xeon Phi if it hasn't already been copied, and execute it on the other side on the Xeon Phi. And then when it's all done, you'll get your x back on the host side, and your data goes back and forth just fine. And that's essentially how it works. That's just an overview. I recommend looking at these slides, looking at the examples. Take a look at the book that I talk about a lot, Intel Xeon Phi Coprocessor High Performance Programming by Jim Jeffers and James Reinders. They've got a lot of really good examples in here talking about exactly what I was just discussing. They've got code examples and done a very nice write-up about it, and that should help you get going.